My name is Brage Kristoffersen. I'm a BRU21 PhD candidate. The sponsor of my project is Equinor, and the title of my project is Assisted History Matching, the Reservoir Model Update and the Production Optimization. One of the fundamental issues with a reservoir engineering is that there are very few direct measurements of the reservoir itself. Instead, we have to rely on indirect measurements and estimations to better understand the subsurface. This could include seismic interpretations of properties and saturations of oil, gas and water, or it could be sensors that measure the production stream or the observed pressure within the reservoir. In a process called data assimilation, we combine this information. We try to fit the simulated values with the observed values to create a numerical model of the current state of the reservoir. We use this model for production forecasting and decision support. Our research group is focusing then on this last part. We help operators find new opportunities and assess the production potential of existing assets. To that end, we created the optimization platform called FieldOpt. It is a platform that we aim to increase the level of automation within the optimization procedure and to better evaluate decisions that are being made and decisions that have been made. I have been able to work with the well placement problem. It is a very difficult problem due to the fact that there are many non-linear flow dynamics within the reservoir. I have developed what we call the automatic well planner. It is a procedure that replicates a geo-steering operation within a numerical reservoir simulator. It helps engineers find a good well configuration faster by increasing the feasibility of each solution candidate. Here we see the top layer of a synthetic oil and gas reservoir. The lighter colors indicate properties that we want to include in our trajectory, while the darker colors are things that we would rather avoid. A well is generally described in 3 dimensions, but from the lateral coordinates of the heel and toe we can make a cross-section. This cross-section is essentially what the trajectory will penetrate. The simplest way of describing a trajectory is by making a straight line from the heel to the toe. It is convenient because it is a low dimensional description of a well, but it does not discriminate whether it's within or outside of the reservoir itself. We enabled the AWP to recreate this trajectory, here shown in red. You can see that it, instead of going outside of the reservoir like the straight line in orange, it tries to situate the well in the brighter areas of this cross-section. Here is a short animation of the AWP doing or recreating a trajectory. The blue dots are what the AWP is observing, while the orange line is what it's trying to replicate or improve upon. We can see here that the trajectory developed by the AWP, shown in red, penetrates the brighter areas to a much higher degree than the orange line originally did. In many studies done with the combination of different optimization methodologies and different versions of the AWP, we can see that the time to convergence for some algorithms reduces, while the NPV, or the net present value, our objective function, increases. If you want to find more information about the automatic well planner, you can read the paper An Automatic Well Planner for Complex Well Trajectories, while new iteration of the methodology will be made available soon. Thank you for your attention.